Welcome back. Namaskar. So this was the last slide where we were discussing about the passive continental margins and active continental margins. So if we there is one more important topic which I'll discuss towards the end of this uh, part, and that is related to your paleomagnetism. But let us see further ahead the distribution of the earthquakes and again the volcanoes and all that. Okay. And now the dynamics of the plate, as we have already discussed about that there are areas where you are having subduction going on, and there are areas where you are having the spreading centers, and there are two types of subductions which are been seen. Okay, and third area is that you are having the plume activity, or the we can say mantle plume, or the hot magma which is anchored below the plates, and if the plates are moving on top of that, that will result into, or that will experience the volcanic eruption other than the subduction zones. Okay. And the best example which we have seen was your Hawaiian chain of islands. Okay. Now something very similar also happened to the Indian plate when it started drifting, moving towards the northern portion of the equator. Okay. So this part we have already discussed about that. You have for the mantle plumes, you have having the continental uh, subductions, continental oceanic subduction, and oceanic subduction. So subduction zones, if we look at, then in 1979, Ida and Kanamori proposed two end member types of subduction zones. Okay. So one is the Chilean subduction zone, and this subduction zones were classified based on at what angle uh, the, uh, the the plate which is subducting below the overriding plate is going down. Okay. So they have they this looked at it, and then they talked about the that whether it is shallow dipping or not. Okay. So this is Chilean type subduction zone, and this type of subduction zone are basically dangerous in the sense because they are having potential of producing mega earthquakes. Okay. So what features you will see over here is that the overriding plate will have back arc compression and uplift which is going on. It will also have in the front over here that you will have the accretion prism, and then you have the shallow trenches. Okay, you will not will come across the deeper trenches like what we have seen the example of Mariana Trench. And due to this area which is in large area is in under friction, you will see this activity, that is your back arc compression uplift, as well as the back outer arc on the subducting plate will bulge. Okay. So there will be deformation in both on both the sides, that is on the subduction subducting plate as well as the overriding plate. And mostly it has been seen that why this shallowness is has been encountered in terms of the subduction plate going down is because of the young thin hot buoyant lithosphere. So it is not very dense in the sense. Okay. So if you are having, like for example, if you are having the subduction the oceanic plate which is more denser, then it will have a higher angle. Okay. But if it is less denser, young, then you will see a sort of shallow subduction going on. So the larger area will remain in contact between the overriding plate and the subducting plate, and this can produce mostly shallow earthquake and mega earthquakes. Okay. So Chilean type subduction, we see what we have, the young buoyant lithosphere which resist subduction and result in shallowly deepening seismic zone. Seismic zone where I have marked. So this will be the area where it will keep producing the earthquake. And one of the best example of the Chilean subduction zone, the associated earthquake was 1960, one of the largest which was recorded on this planet. Okay. So shallow trenches will be there, great thrust earthquake, and back arc folding or and thrust faulting you will see. Okay. Thrust faulting, the terminologies we will come across later on also, but I will just try to explain that. So, this is mostly we will see in the compressional tectonic environment. So, mostly what we see is that the one of the block is moving like up with respect to the another one. Okay. So, further if we see, so one this is the Chilean type subduction zone, and if you see this in Andaman, this also has the Chilean type subduction zone. The plate is not having the dip, or it is not having steeper dip, it is having shallower dip. Okay. Now, Mariana type subduction zone, as we have already gathered that point that this has an deep trenches. Okay. And the angle will be steeper. Okay. Now, why this is the angle is steeper? The reason is that old thick uh, oceanic crust is comparatively denser as we compare to the young, thin, and lighter uh, in terms of the density. Okay. So, here there will be a sort of an rollback, uh, what we call, okay, because of the steeper plate which is subducting down, the angle of the plate. Okay. So, that will result into a sort of a rollback here, and mostly what we see that not major earthquakes will be coming across here. So, because the interaction between the two plate is not much as what we have seen in the shallowly dipping plates. Okay. So, subduct old dense lithosphere which readily sink because of its weight and density. Okay. And Mariana type subduction zones are characterized by steeply dipping seismic zones, deep trenches, and that is because of the rollback also, and absence of what we can say the great thrust earthquakes. Okay. But there you will see in great earthquakes, and why we are saying that the Andaman Nicobar area and the area which is going towards the Sumatra side is in like can be categorized under the Chilean type subduction zone because it has produced mega earthquakes. Okay. And recent one we have 2004 is the example of that. Okay. 9.1 to 9.3. So, Chilean or the convergence related to compression mode, and Mariana type or the convergence related to extensional mode. Okay. So, this is another one we see, because what we have seen here that this area in your Chilean type shows bulging, but here you see an extension because of the rollback of uh, this region related to your steep deep dip of uh, the subduction. And this is what is an example you have, and very clear indication of the extension which is going on over in this area, and you are having the subduction, and the deeper portion is been shown with the very dark color over here, as we have also discussed in before, that deeper portions where a light does not reach, and or maybe it is not reflected back, hence it is absorbed. So, we do not see a sort of an subduction here. Subduct old dense lithosphere which readily sink steeply dipping seismic zones. Okay. And you have back arc extension which you will come across in this part. So, this is an example which shows that how the earthquakes are been seen, and this is known as Vadati-Benioff zone, and that will result into the focus of the earthquake or the occurrence of the earthquake throughout the plate boundary. Okay. And that the earthquakes can go as deep as 700 kilometers. So, this again which shows that you will come across the in deep earthquakes which goes below 700 kilometers, intermediate earthquakes and you have shallow earthquakes over here. Now, coming to the other part, which I told that I'll try to cover this part, which is related to uh, the the movement, or we can say the how the earth moves or rotates. Okay, what are the reasons for that in terms of the interior of earth and all that. Okay, so earth as a geodynamo, because it produces magnetic field, it's keep rotating, and the rotation is there. However, there are few things which are which, if time permits, I'll discuss that what are how this axis changes, how this rotations are been slowed down and all that, and what are the parameters or the important points which results into that, and that can result also into the change in the climate. Okay. Now, this if you consider that the Earth's magnetic field is much like the field that would be produced if a giant magnet were placed at Earth's center with slightly inclined, because this is 111 degree. What we have is the inclination of the axis. Okay, that is from the axis of rotation. Okay. Now, mostly what has been we came across that how this the inner core and the outer core, because this is a discussion between the inner core and the outer core. Outer core is liquid, the inner core is not, it is solid. Okay. So, Earth's center resembles a typical permanent dipolar magnetic bar. Okay, as you see here. Okay, so it will be very much similar to the dipolar magnetic bar. Okay, and uh, the so this hypothesis can be easily rejected. Okay, so there were several questions which arise before uh, concluding this, and of course this has been proved by the experimental setup. But this question was there that if the outer core, which is liquid, if it is responsible, because wherever there is an the hot uh, portion is there in the Earth's crust, or in the Earth interior, uh, and the crust is also floating on the asthenosphere, where asthenosphere is like creating convection currents. Okay, so the inner outer core, which is liquid, okay, and that is acting as an the responsible for the magnetic field, then the hypothesis said that how it is possible that that portion is able to create such a strong magnetic field, because at 500 degrees any permanent magnet will be destroyed. And if you recall and remember that the temperature increases as you move towards the interior of Earth, and it goes more than 5000 degrees centigrade. So, even at 500 degrees centigrade, it will be destroyed. Okay. So, we know that the temperature in the Earth deep interior are much higher, thousands of degrees at the center. Okay. So, the question remains that at 500 degrees all magnets will be destroyed. So, then how this layer or the unit is keeping itself producing the magnetic field. So, unless the magnetism is constantly generated, that means it is destroyed again, it is been generated again and again, it cannot be maintained. Okay. So, that was those were two questions. Okay. One is that the permanent magnet is destroyed at about 500 degrees centigrade. However, the temperature in interior of Earth is of like the scale of thousands of degrees. Okay. So, unless and until it is not constantly produced, it will not be able to maintain the magnetic field. So, scientists suggested a theory that heat flowing out of Earth's core causes convections, that is convection currents, that generates and maintain the magnetic field of the Earth. The question 1 was, a magnetic field is created by convection in the outer core, but not by convection in mental. Okay. So that was another question which was been because it is related to your geodynamo what we are talking about. So it has been suggested that the outer core is primarily made up of iron, which is very good electric conductor, whereas the silicate rocks which are close to the crust, that is in the upper mantle and you can say that part, okay, they are mostly made up of silicate rocks, okay, which are poor electric conductor. So the convection motions are a million times more rapid in liquid outer core than in the solid mantle. Of course, asthenosphere is partially molten, but that is also comparatively it has been considered as not completely liquid. Okay, so this was one of the answer for that the material also plays an important role in generating the magnetic field. Okay, so this rapid motion stir up electric current in the iron to create geodynamo with strong magnetic field. So this was one of the answer to the question which was been raised. Okay. Now further, if you look at that, this what we were talking about, that outer core is liquid and the inner core is solid. So what are the reasons for that? Okay, and since we know that the temperature at the interior of or the center of the earth is almost close to 6,000, not 6,000, 5,000. This is the depth here. That is 6,000 kilometers, but the temperature goes up to 5,000 degrees. Okay, so why this outer core is liquid, okay, and the inner core is solid. Okay, so the geologist basically puzzled by the existence of the solid inner core when the temperature inside the earth increases with depth. Okay, it has been estimated that the temperature rises from 3,500 centigrade at the core mental boundary. So this is the core mental boundary. So there what we are having is around 3,500 degrees centigrade or so, and further it goes like up to 5,000 degrees centigrade in towards the interior of earth, that is towards the outer core and the inner core side. Okay, therefore if the inner core is hotter, okay, so if the inner core that we are talking about, this one inner core is hotter, how could the inner core be solid while the outer core is molten or liquid? Okay, so the mystery was eventually solved by the laboratory experiment on iron nickel alloy, which showed that the solid nature was due to high pressure rather than the temperature at the center of the earth. So to the pressure increases so much that it does not allow the inner core to remain in a liquid form. So that was one of the conditions or the reasons which were been given, and this was been sorted out based on the experiments. Okay. So the temperature, the of course the temperature rises around 5,000 degrees temperature, and then the pressure, if you see, it goes up to like around like your 400 gigapascal. Okay, and that was the reason which has been given for your solid inner core. Okay. Now, so the few reasons which were been given that the convection currents are been produced very fast, and they will be of much faster as compared to what we see in the asthenosphere, and that is one of the reason for the generation of the magnetic field of the earth. Okay. And another part which has been also discussed, that experimental on basis of the experimental uh, experiments which were been conducted, which suggested that the pressure plays an important role for keeping your inner core solid, whereas the outer core is liquid. Now, there was another theory which came up, and that was we partially we discussed this when we were talking about the magnetic reversals and where the spreading centers mainly were been seen. Okay, so what they were able to identify was that the minerals, magnetic minerals, were not showing the same alignment. Okay, so and that was what we were also talking about, the magnetic tape. The sea floor spreading is like a magnetic tape or the recorder. Okay, where you have the reversals of the magnetic the oriented, like minerals which are oriented along the then existing magnetic field. Okay, so that what we they say that magnetic reversal. Okay, so magnetic reversal is like you are having, if you have north south, what we are having now we've been termed as the normal polarity, and the reverse polarity where the north becomes south and south becomes north. Okay, so this has happened in the past, and that is what we call the paleomagnetism. Okay, so the term paleomagnetism refers to the study of magnetism of rock at the time their magnetic signature formed. Okay. So, for example, all magnet for if you are having this is north and this is south, so all magnetic minerals will be aligned in this direction with the north. Okay, but if this changes, then you are having the alignment is different, with this north and south. Okay. So, this reversal was been identified the spreading centers, close to the spreading centers. Okay. So, the cause of magnetic reversal is not known. Okay. And again, it is also related to your the generation of magnetic field and rotation of your earth. Okay. And this is also connected with the geodynamo process what we were talking about. Okay. It is not well known, but it is related to change in the convection moments of liquid material. Okay, in the outer core, processes occurring in the inner core area. Okay. So, reversal in Earth's magnetic field are apparently random, occur on average every few thousands years, but still it is not fixed that it will happen, but it is related to the changes in the convection moments. Okay. So, that means either the convection currents are slowed down, which reverse this the magnetic field and reverse the poles, that is south to north and north to south. That may be one of the reason. The change in polarity of Earth's magnetic field takes a few thousands years to occur, which is in geological term we can say it is very short time. Okay. So, this is what they have found, that they have positive and negative anomalies. Okay. Over the time they have come across this, and so in future also this is going to happen. Okay. So, that is what we call polar wandering, and also we call the magnetic reversals. Okay. So, we will stop here and we will continue the next lecture talking about the significance of seismicity and what is the importance of your the alignment of earthquakes in particular regions, and we will slowly come down to the importance of the historical seismicity also. Okay, and that is what basically we want to see, that how earthquakes or which have occurred in the past during the historic time or the prehistoric time, and also during the modern era, how we can take that into consideration, and how that information which is like prehistoric or historic earthquakes. Okay, because we don't have the epicenters of the historic and prehistoric earthquakes, but based on the historical documents and the sites or the we can say the ancient sites, okay, or the ancient settlements, studying those sites, how we can interpret and how they are they play important role in understanding the overall hazard which is posed by that region. So we'll talk about that. Slowly we'll come down to Indian side, few examples from the Dead Sea area we will discuss, and we'll see that how they play an important role in seismic hazard assessment. So till then I'll stop here. Thank you so much. Namaskar.